All right, so we just discussed the three models of light. The particle model, the wave model, and the new model, the photon model. So now we want to kind of shift gears. So this is a French physicist, Louis de Broglie. And he had this incredible radical idea. He said, look, consider light. Light certainly has wave-like characteristics, but it also has particle-like characteristics. Well, therefore, if light has both particle characteristics and wave characteristics, he said all particles, even particles with mass, like electrons, should also act like waves. Now, he didn't just stop there. He actually came up with a formula. He said all particles, massive particles he's talking about now, massive particles should have a wavelength. I mean, if they act like waves, they should have a wavelength. And this is his famous formula. The wavelength of a massive particle, like an electron or a proton, whatever, equals, this is Planck's constant again, it's a super, super tiny number, over the mass of the particle times the velocity of the particle. Now, when you look at this equation, you should realize this is totally insane, because wave property, particle property. And what did we learn a long time ago? Waves and particles are completely different. Well, that kind of trashes that idea, doesn't it? Because here you have a wave property and a particle property in the same equation. Now, he included his ideas in his PhD dissertation. And he turned it into his PhD committee, and they didn't know what to do with it. And so they sent it off to Einstein, and Einstein gave it the thumbs up. Well, he approved it. Okay, so let's calculate some of these wavelengths. So let's do a fast sprinter. So a human being, a fast sprinter. I mean, have you ever noticed a wavelength of a person or a rocket why not? I mean, you haven't, so why not? So let's do a fast sprinter. So the wavelength equals h over mv. So h is 6.63 times 10 minus 34 joules seconds. All right, let's say, just to make the numbers nice, 66 kilograms, and velocity 10 meters per second. Not world class, but not bad either. So that's about 10 to the minus 36 meters. Now, I'm sorry, that's just way too small. We don't know how to measure something that small. I mean, atoms, like nuclei, 10 to the minus 12 meters, something like that. So this is just too small. And that's why we never, that's why you never see it in the real world, right? It's just too small. Okay, now let's do a fast electron. Fast electron. So lambda, okay, so again, 6.63 times 10 minus 34 joule seconds. Okay, the mass of an electron in kilograms is 9.11 times 10 to the minus 31 kilograms. And we're going to say speed of light. Now we know it's not going the speed of light. It's going like nearly the speed of light, like 99.9999, but let's just say speed of light. So approximately speed of light. All right, you do that, and you get 2.4 times 10 to the minus 12 meters. And that's easily measured, easily measured. So what does that say? It says that if we do some experiments with fast electrons, we should be able to see the wave-like nature of an electron. Well, what kind of experiment should we do if we want to see the wave-like nature of an electron? Do the double slit, right? Do the double slit experiment that we've talked about over and over and over. So let's do that. All right, let's do a double slit experiment with electrons. And so you have a detector for the screen, and it detects the single electrons. So you start out here, you just see the little electrons, right? Then you wait a little bit longer. You wait a little bit longer. Uh-oh, what are you seeing? What's beginning to develop? You wait a little bit longer. And bingo, you get a wave interference pattern with electrons. Now that's crazy, right? Because an electron is this little particle that orbits the nucleus. Well, guess what? It acts like a wave, as de Broglie predicted. Crazy. All right, here's kind of a fun thing here. And I already gave you the answer, so you don't have to vote. Okay, double slit interference of electrons occurs because each electron goes through both slits. That's the correct answer. Now you're probably saying to yourself, well, that's insane. How can a single electron go through both slits? Well, on the other hand, the electron acts like a wave. So in order to get interference, the wave has to go through both slits. So that's basically equivalent to saying that the electron goes through both slits. It's even worse than that. So people have done the double slit experiment, and what they've done, they've shot one electron at a time. So shoot an electron, wait however long you want, shoot an electron, wait, and you just wait long enough, and guess what? You still see an interference pattern. Now if that doesn't blow your mind, I don't know what does. So here, with a weak electric beam, or we can send one electron at a time through the apparatus and still observe an interference pattern, or an interference in the resulting pattern of electrons. So that's totally insane, but yet it's true. All right, so a little history for you. So in the past, I've talked about Richard Feynman. I've mentioned him. He was a Nobel Prize-winning physicist who basically came up with his own way of doing quantum mechanics. So he was a genius. So he was employed at Caltech, which is where a lot of the Nobel Prize-winning physicists are employed. And typically, if you're a researcher like Feynman, you don't usually teach classes, maybe one a year, some upper-level graduate graduate-level class or something like that. But anyway, so years ago, they convinced Feynman to teach freshman physics, which is kind of like unheard of. That just doesn't happen. And so he did it. He did 3 semesters worth, and so these are the famous Feynman lectures on physics. So somebody transcribed his lectures and edited them and all that. And he actually talks about this in one of his freshman level physics classes. He basically says, this is life. This is how it actually is. It doesn't make a bit of sense. It doesn't agree with our experiment. With our experience, it does agree with experiment, but it's true. It's actually true. And he uses that as an example to show how quantum mechanics is weird or strange. Anyway, so you can look it up, right? Look up the lectures on physics from Feynman, and he has a whole chapter on this double slit experiment with electrons. Okay, so where does this all lead? The wave nature of electrons. Where does this all lead? So this is a very famous example that's always done in quantum mechanics. It's called the particle in a box model. So just pretend it's really narrow. So we want a one-dimensional box, right? So a one-dimensional particle in a box. So all right, so we have a classical particle bouncing back and forth. You can't get out of the box, right? So the particle just goes back and forth, back and forth, back and forth. Now, classically, the particle can have any velocity, right? Any kinetic energy. There's no limit. Do whatever you want to do, However, if the electron, or I shouldn't say electron, if the particle acts like a wave, then, and it's confined to the box, that's the important thing. If the wave is confined to the box, therefore, the waves reflect back and forth, back and forth, back and forth. Now, where have you heard that before? Where do we have a wave? You start it off and it reflects back and forth, back and forth, back and forth. It's a standing wave, right? It's a standing wave. Okay, so there you go, all right? So it has to be this way, right? Because it's confined, right? The particle is confined to the box. And so the waves just reflect back and forth, back and forth, back and forth. Now, when we talked about air columns, we had close, 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 open, and open, open. So which one is this? Well, you know, this is a displacement node, right? No oscillation, so is that. And so this is a close, close. All right, so a reflected wave creates a standing wave, and hopefully you remember that this is exactly what we saw. Just look at the blue curves, the displacement curves. That's what we saw in a closed, closed air column. So let's work that and see what happens. See where it leads to. All right, so I'm just going to repeat what we did a long time ago. So this is a half a wavelength. This is one wavelength. This is 3/2 wavelength. So what did we learn? We did this before. So the length of the column is some integer n times lambda over 2. That should be no surprise. And so therefore, we can say that lambda n equals 2L over n. And again, n, 1, 2, 3, da, da, da. All right, but wait a second. What did de Broglie say? De Broglie said lambda equals h over p, which is h over mv. So let's combine them. Let's put this equal to this and just see what we come up with. So we'll have 2L over n equals h over mv. All right, let's solve for v. Let's solve for the velocity. So we're going to have velocity equals nh over 2ml. And we could, just like we always do, we can put the n outside, make it look nicer. There. Okay? So if you want, take a little subscript there. So that's the possible velocities of this particle in the box. Now wait a second. Did you hear what I just said? This is the possible velocities of the particle of the box. Now classically, a particle can have any velocity, right? Here it says nope. The only possible velocities are v1, which equals h over 2ml, v2, which equals 2h over 2ml, v3, which equals 3h over 2ml, and so forth. So that's another thing about quantum physics, right? That's why the word quantum is there. We say that the velocity is quantized. There's only certain values that are possible. Well, let's keep going. Let's get the energy, right? Okay, let's get the kinetic energy, right? The kinetic energy, because that's all we care about. So the kinetic energy, as you know, is 1/2 mv squared. So you do that, and you're going to get, so n squared, right? Then we got to square that thing. So that squared, h squared. We're going to get a 4 when we square it, but we're going to have a 4 times 2 is 8. So 8ml squared. Now, let's call this, that's an h by the way, let's call this E1, right? Because that's what it is, all right? It's the energy of the one state. So this is just n squared E1. Now, once again, that's called quantized energy. So you see, when you say that the particle acts like a wave and is confined in a box, the energy can only be certain values. It can't be continuous like in classical physics. It can only have certain values. So we say that the energy is quantized. Right? Quantized. Just like eggs. You go to Foodland and you say, I want a half an egg. The person looks like looks at you like you're nuts, right? Eggs only come in units of 1, 2, 3, you know. Well, energy is quantized. There's only certain values of energy. So that's something that you see in quantum mechanics. Okay, so quantized energy, completely non-classical. So E1 is h squared over 8 ml squared, and En is n squared over E1. And again, n is just that number, right? Just the index. You know, we've seen that before. By the way, we're going to see this again in a future chapter. So just trying to remember it, all right? Particle in a box. All right, particle in a box, quantized energy with this formula, because we're going to see it again. Now this is kind of a nice, I like this a lot. All right, just as I can't stand between two adjacent steps, right, an electron can't exist between two energy levels. I think that's nice, okay? So energy is quantized. All right, now, where am I? Lost. Okay. Now, let's go back. What is it that led to the energy quantization? It's the confinement, right? It's the fact that the particle was confined in that box. All right, think about an atom. Are the electrons confined? Well, yeah, they're certainly confined, right? You know, they're confined to orbit the nucleus. So therefore, should we expect the energy to be quantized? Well, yeah. All right, and that's what, okay? All right. Okay, now we want to talk about what's called the Bohr model of the atom. So Niels Bohr was one of the originators of quantum mechanics. However, but you have to understand something. So here's classical physics. Here's quantum physics as we know now. So the Bohr model was kind of in the middle. So like I say, he was one of the originators of quantum physics, but some of his model was shown to be correct. Some of his model was shown to be incorrect. But so let's just say he bridged the gap, right, between classical and quantum. So it's worthwhile to talk about his model. So let me remind you of some things. Remember that chapter that we just spent like an hour on, 37, I think? It was before we did special relativity. And we talked about the fact that you shine light through a prism, it splits up into the spectrum because different wavelengths have different indices of refraction, different colors, different wavelengths. And then we went through this whole thing, remember, how you shine light through a prism and you get what I just discussed. And then the light goes through a cloud, and lo and behold, some of the wavelengths of light are absorbed. And then if you just look at the cloud without the light, just the cloud, you see some bright lines. You expected to see darkness here. You're not looking at the light, right? You're just looking at the cloud. There's no light. So you expect this to be dark, but it's not. So hopefully you remember when we discussed this that there was no understanding at all what was going on here. And then there was also this strange fact that these absorption lines perfectly match these emission lines, and that was a total mystery. And here's more of it. Total mystery. Every element has a unique spectrum, just like people have unique fingerprints, right? Every element has a unique spectrum. Okay, so that was all mysterious. Now, so this is we call this the solar system model of the atom, right? The solar system model. This is the classical solar system model of the atom. And this model cannot explain those spectral lines like I just said. And this model can't even explain why atoms are stable. What am I talking about? Well, in Physics 220 we learned that when a charged particle accelerates, which means either going faster or slower or going in a circle, like these electrons are doing, when a charged object accelerates, it radiates energy. It loses energy. So if you work it out, you know, the fact that the electrons are accelerating right around a nucleus and they're giving off energy, they're emitting light, within, I think, like a millionth of a second, the electrons would crash into the nucleus. So basically, classical physics is clueless. It's completely impossible to explain atoms just using classical physics. So that's why Niels Bohr came up with his model of an atom. All right, so let's just go through his model. Okay, number one, Bohr said, look, atoms are stable, right? So the electrons don't crash into the nucleus. So therefore, there has to be stationary states. And these stationary states have to have, certain energies. So you talk about quantized energy. And so this is called the energy diagram for hydrogen. And so this is like the n equals 1 state with this energy, n equals 2 state with this energy, n equals 3 state with that energy, and so forth and so on. So what he's basically saying is electrons can only exist in these states. In other words, it's totally impossible to have an electron with like E equals minus 5.2 or something like that. It's either that, and so on. All right? And they're stationary. They don't crash into the nucleus. Okay, so we call this, okay, so 1 state, 2 state, 3 state, and so on. Then Bohr, okay, so, all right, so he came up with this because, I mean, everybody knows matter is stable, right? So there has to be stationary states. I mean, it's as simple as that. Okay, number two, he said that an atom can jump from one stationary state to another by either emitting light, which is energy, or absorbing light, which is energy. And of course, the light has energy hf, right? Remember Einstein, photoelectric effect? So the energy of the photons is either absorbed or emitted is hf, and that's the change in energy from one level to another level. And that's the only way. You can't go from here to here because there's no such thing as here, right? So, okay. All right, so now what's the big deal about that? Okay, so that means you can have, well here, this is the best way to show you. Okay, so let's say, so this is the, here's the electron in this particular level, and then let's call this the ground state, so the lowest energy electron. And then here's the next highest. By the way, we call those excited states, right? So this is a ground state, like the couch potato state, and this is the first excited state. And these are the, like it says, these are the allowed orbits. Okay, so let's say you have this excited state electron. Let's say it's an n equals 2 level or something like that. And then you get, and then, you don't want to stay excited very long, right? And so in order to go to the ground state, the couch potato state, where most people want to go, just like electrons, yeah? And so the electron, the only way it can go from the excited state to the ground state is by emitting a photon. And that photon has to have exactly the energy, this state, the difference between this state and this state. It's the only way. So in other words, if the energy is unique or quantized, well, remember that super important formula. So for light, E equals hf, which equals hc over lambda. So if it's only a certain energy, certain frequency, certain wavelength, right? So it's only going to be certain wavelength of light or certain frequency of light that is allowed. So this photon here can only have one particular energy, the difference of this state and this state. Okay, let's read it. So the electron jumps to a lower energy stationary state and emits a photon. Okay, let's do it the other way now. Let's say here we have this lazy bum electron in the couch potato state, the low energy state. And then there's an approaching photon. And what happens is that the photon gives all its energy to the electron. Does that sound familiar or what? And so the electron jumps up to the first excited state. So the electron absorbs the photon and jumps to a higher energy stationary state. But the important thing is, once again, the energy of this photon has to be exactly the energy difference between this state and that state. No other photon will do it. Now, come on, that explains this, right? I mean, here, you know, here, photons are being absorbed, right? Because you're not seeing any light here. And it only happens at certain wavelengths. In other words, it only happens at certain energies, which is exactly what we have here, right? This is absorbing a photon of a very specific energy, which means specific wavelengths. Here, they're being emitted at certain wavelengths only, or certain energies only. Well, that's this. Okay, so there you go. Okay, so atoms emit and absorb a discrete spectrum. Discrete means like this. This is continuous, right? This is discrete. All right, only certain wavelengths. Okay, and look, let's go back here. You know, so the photon, so this photon, to get this guy to go from couch potato to first excited state, that's the same energy as this photon, right? To go from first excited state to couch potato state. So this photon has exactly the same energy as that. So the emitted photon has the same energy as the absorbed photon. Well, golly, where have we seen that before? Right there, right? Right there. Okay, so the absorption wavelengths are a subset of the wavelengths in the emission spectrum. Okay, so all right, and then again, you know, every element has a unique energy level diagram, like I showed you the one for hydrogen. Well, the one for sodium is different. The one for, well, whatever. Every element has their own unique energy diagram. Well, that means that they're going to have their own emission spectra, right? So Bohr explained that too. Each element has a unique spectrum. So Bohr's doing pretty well, right? He's explaining a lot of things that people were clueless about. Okay, there's also something called the inelastic collision. Remember that? Two rotten grapefruits, so the kinetic energy is not conserved. And so here's just an example. So here's an electron in its couch potato state. Here's an approaching whatever, and it just gives off some of the energy. So this particle transfers energy to the atom in the collision and excites the atom. Okay, that's part of it too. It's not a big deal. Okay, so you can also, okay, look. So if this is going to go from low to high, eventually it's going to go from high to low and emit light, right? And so emission spectra can be produced by collisions as well. So this is not the only way to do it. This is another way to do it. And n equals 1 is called the ground state. I call it the couch potato state. It's the lowest energy state. So most of the atoms are in the ground state most of the time. Okay, so that's the general Bohr model of the atom. But now what we want to do is we want to apply it to, you know, a real atom. Now think about it. If you just came up with this great model, which seems to be working, but now you want to apply it to a real element, right? So which element are you going to start with? Uranium or hydrogen? Well, it's pretty obvious, right? You can start with the simplest one possible. So now what we're going to do, we're going to apply this Bohr model to the simplest element that there is, and that's hydrogen. So let's quit, and we'll do that next.